In this video, we'll learn about Dalton's law of partial pressures, which states simply that the total pressure in a mixture of gases is equal to the sum of the pressures exerted by each individual gas. So if you have several different gases in a mixture, and you know that their total pressure is however many atmospheres, um, that sum is equal to the pressure that is exerted by, say, the neon in the mixture, plus the pressure exerted by the oxygen in the mixture, plus the pressure exerted by the nitrogen in the mixture, et cetera, et cetera. And another thing that we'll need to know to help understand the law of partial pressures is something called the mole fraction, which is that the moles of any specific gas divided by the total moles of gases in a substance, that is the mole fraction. And we'll get into that a little bit further pretty soon. So um, I want to show an example of how Dalton's law can play out in a very common laboratory scenario. So let's say we have a reaction mixture and there's a gas produced in this reaction. Now, if you just let the gas bubble out, you'll never see how much gas is produced. So what many chemists do is they collect the gas by leading it through a tube, and they allow it to bubble up into an inverted container that has some volume marker on it. And what happens is, if that inverted container it's full of liquid initially, then the um, the gas produced from the reaction, as it comes up, it of course will want to float because it is of low density, and so it will go to the top and it will actually push out the water from this container. And as more and more gas is produced and bubbles up into this container, the water level will get lower and lower and lower. And eventually, when the reaction is done, you'll be able to determine the volume of gas produced, which is just the volume from the top up until wherever the marker is that the water level has got to. Um, and so that makes it pretty easy to tell what the temperature, sorry, what the volume is of the gas. Temperature is easy to get as well. And if you measure the pressure, great. You can use PV equals nRT to figure out the moles of gas collected. But a common mistake is that the pressure, people forget that the pressure um, noticed in the container is going to not be simply equal to the pressure exerted by the gas produced in the reaction, but it's actually the gas plus vapor pressure. Vapor pressure, of course, does exist. There's a certain amount of water vapor above the surface of this water, and that will play into your total gas pressure. So let's do some problems. First of all, a nice simple one. Calculate the total pressure of a mixture of gases containing 1.0 atmospheres of helium, 2.0 atmospheres of argon, and 1.5 atmospheres of xenon. By the law of partial pressures, the total pressure is equal to 1.0 plus 2.0 atmospheres plus 1.5 atmospheres. And what we get is 4.5 atmospheres of total pressure. And couldn't make it any easier than that. Um, Now, this next problem is based on the previous scenario. The previous scenario where there is gas collected over water. So let's say that the total pressure noticed is equal to 753.9 millimeters of mercury. Well, if it's equal to 753.9 millimeters of mercury, you might want to use PV equals nRT and just go straight from there to figure out your moles of gas. But actually, you need to modify the pressure because that is a total pressure reading. And apparently, at 25 degrees Celsius, 23.8 millimeters of mercury. Well, 23.8 millimeters of mercury is the vapor pressure, leaving the pressure exerted by the hydrogen gas collected equal to only 730.1 millimeters of mercury. And I suppose that, yeah, it would be 730.1. This would be precise to the tenths. And that is that. So finally, we move on to a third problem. A mixture of gases exerts 800 millimeters of mercury of total pressure. It contains 1.0 moles of argon, 2.0 moles of nitrogen, 0.5 moles of neon, and 0.5 moles of helium. So what I'm going to do is I'm going to figure out this mole fraction. And that is 1.0 moles of argon divided by moles of argon plus moles of nitrogen plus the moles of neon plus the moles of helium, which is 1.0 over 4. So my mole fraction for argon is 1 over 4. And my mole fraction for nitrogen is going to be, sorry, I'll write it here. For nitrogen, it's equal to 2 over 4. My mole fraction for neon is equal to 0.5 atmospheres, 0.5 moles of neon over 4.0 total moles. And my mole fraction for helium is equal to 0.5 moles of helium divided by 4 moles of total gases. So what I can do is I can say essentially a quarter of the total pressure, 1 over 4 of the total pressure, is attributed to argon. So I can take that 1 over 4 and multiply it by 800 point, and that is in millimeters of mercury. And what I get is 200 point millimeters of mercury that are exerted by the argon. In the case of the nitrogen, I'm not going to show out all the math for this, but it's just 2 over 4 times 800 gives us 400 point millimeters of mercury. For the neon, it's going to be half of what argon was, 0.5 over 4 times 800. That's 100 point millimeters of mercury. And for helium, it's the same. So what we find is that out of our 800 millimeters of mercury, that's the total pressure, 200 millimeters of mercury were exerted by the argon, 400 by the nitrogen, 100 for each of the neon and the helium. And that adds up to our 800, and it gives the appropriate amount of pressure attributable to each of the 4 gases in the mixture. Hope this video has been helpful. Feel free to leave any questions or comments in the comment section below. Thanks for watching.